So right now we are not doing any control, so this is just fixed in place basically. Like 200. Then you see, okay, from 500 now, because it's around 500, it's moving down to 200, which gives a bit of overshoot because because of the constant value. But then we approach this steady state, and it's not actually converging to the actual target value due to friction and other imperfections in the system. So this is the proportionality only. If we, for example, now go back to 512 with some smaller values, then you will see different convergence. But yeah, you see the steady state is not the target. So now we have to add the integral and the derivative part. We actually developed 3 wind-up strategies. The first one for the integration part. The first one is in the read input method. We put it there because then if we read new things, like for example a target, then we basically reset the accumulated error so that it doesn't have to work with any predefined accumulated error. So that's the first wind-up strategy that we implemented. Then, if we look into the actual code, every interval it does this, it sets this movement, right? And first it accumulates the error, so delta t times the error. So this is the second wind-up strategy. We don't want it to kind of increase, right? We want to set a maximum accumulation. And we set it to this value right here in the code, 20,000. And then the third one is this. It basically checks if the deviation to the target is less than some error value that we set, then we should just say it's correct, because it will get close and then it shoots over, and then it will go close to the line again, and then it shoots under, and it will keep on doing that fine, and we just set that value to our value of 3. So those are the wind-up strategies. If we actually run this now, you can see we have set this to 320 initially. We are going to use the value of 0.5 from the proportional part. So if we first set this to a high value, let's say maybe this, then you can see it has clear oscillations, right? Because the integration part is accumulating, then it's reaching the maximum value. That's what you can see on this horizontal line kind of on the top. And then it goes down again because now it's overshooting and it just keeps on oscillating. So this is not what we want, right? So let's set it a bit lower. Let's set it to like 0.005. Now you can see the oscillation decrease, and it actually hits a perfect target after this. But it's not like a smooth movement. So this is why we will add the derivation part, so you don't have these steps basically. Like it seems like you have steps coming down. Okay, so now we are going to show you the derivative part of the PID tuning. So the derivative part has been implemented here. So the derivative is just a first order approximation. You use the error and the previous error divided by the interval in order to kind of estimate in which direction it's going and to dampen the integration part. So we initialize it to the difference between the target and the current value of the motor. So then, yeah, that's basically x0 or e0. Then we recalculate and we reset the previous error after updating the motor. So now let's show you how it works. Let's set it to 0 at first. So if you set it to 0 and go to 700, you see this overshoot before it reaches the steady state because of integration. Let's go back now, and let's show you what it looks like with the derivative part. So, which has a value of 25 in this case, and you can see that it doesn't overshoot anymore because we cancel out the integration factor and stuff. The rise time is still relatively the same. It doesn't influence reaching the steady state, but it does get rid of this overshoot. But if we set it really high, let's try 50 for example, then you can see the rise time really takes a bit longer to reach the steady state because we are
reducing the influence of the integral.
How we did the tuning process. The way people will repeat this is by, of course, using the same code, the same servo motor, because parameters could be different among different motors, right? But let's set the target to 700, and we're gonna first only use a proportional value. So let's set this to 2. We can see that it kind of overshoots at the beginning, then it oscillates, and then it reaches this steady state. If we set this to 300, for example, then you get something similar. We are going to add a bit of an integral. So we don't know how much yet. We're going to set it to 0.1. That may be a bit much. We don't know. and that is definitely too much. So as you can see, the motor is going crazy right now. So let's try to decrease it even more, and then you can see oscillation, but it kind of dies out in the end. So if we do this to the 700, yeah, you can see it still reaches, and then this is the wind-up strategies that we used, right? That we explained before. It actually reaches the target. If we start adding the derivative, and let's set this derivative to 10 at first. And then we see it's not quite enough, so let's set it to 25 maybe, and then we go to 700. This already looks really good. That's for different value. Maybe you can still see here that it still takes some time for it to converge. So maybe we should try increasing the integral a bit more for the same 700. Okay, so now we see that this is probably due to the proportional part. So let's decrease this a bit more. Okay, this looks amazing already. So for 300 it looks good. For 700 it looks good. 450 it looks good. So you basically have to. It's not always that trivial how to tune, because at some points it may be overshooting and in other cases undershooting, and then you have to see what you would increase. So we set them to 0.4, 0.0022, and 25. The way you tune these parameters is quite non-trivial, and it's really hard to get it just right. Overshoot at some point, which kind of indicates that you could increase the derivative, but then you could also decrease the proportional part, you know, to kind of get rid of this overshoot. And decreasing the proportional part would maybe make a difference in different values. That's why we changed this from 0.5 to 0.4 to make it a bit better for everything, right? So, for example, here we set it to 650, but we still obtain this quite large steady state of 15, and this is probably due to some friction in the motor. It's still, the integral is still winding up, so it should like be minus 20,000 now, the value, but it can't actually add it because the power of the friction in the motor is so large now that it doesn't that it doesn't actually move anymore. If the integral would increase more, it would go back, but we set the cap. I mean, it's not perfect, but it's perfect in many ways. So very quickly about any interesting discoveries that we've made. The first one was about the friction, right? At some points the force may not be enough that you want to apply to actually cause a movement because of friction in the gears, noise, you know. It could be, something could be going on, is going on in the physical process that prevents it from moving. Then the second thing is that there's this black box that we had some problems with at the very beginning, because if you want to move through there, then you don't get any valid information from the measuring device.